So welcome back. So we'll continue our discussion on optical coherence. So today we will discuss the concept of complex analytic signal. So this is a useful mathematical tool, a technique in the study of optical coherence. So why are we keen to introduce the concept of a complex analytic signal? So in physical theories, we typically study the dynamics of real valued quantities like current, electric field, charge density, so on and so forth. However, complex variables render the mathematical calculations much easier. So in quantum mechanics, of course, complex variables naturally enter the analysis, they enter the picture. However, even within the realm of classical physics, introducing complex variables simplify the calculation. So the spirit behind this is the following. So we basically, what we do is, within a classical description, we take a real variable that is of interest, we map that onto a complex variable, do the analysis, study its dynamics, and then once the calculation is over, we extract the real quantity from the real part of the complex quantity. Okay. So the mapping of real random variables, of course, here the random variable is the optical field, which is a random quantity, which is a random signal. So the mapping of real random variables to the complex ones is called the complex analytic representation of the real random variables. So these are purely mathematical quantities. So they don't necessarily carry any physical significance. So we are introducing complex analytic signals only for mathematical convenience, to render our mathematical analysis easier. Otherwise, they don't by themselves carry any physical meaning. So let x of t be a real function of a real random variable t. And let us assume that its Fourier transform exists. So which means I'm sorry. I'm sorry. Those are x of t and x of omega related. So we assume that the Fourier transform exists. Okay. Now, we can do something here. We can split this integrand into two parts, one for the negative frequency and one for the positive frequency. Now, this one, the positive frequency part we denote it by z of t, and the negative frequency part we denote it as z star of t. Okay, and this is the positive frequency part. And this is the negative frequency part. So we have simply split this integral into two parts. Okay, and z of t, this quantity z of t, by definition, is the complex analytic signal associated with the real random variable x of t. By definition. So this is how we construct complex analytic signal, construct a complex analytic signal. So of course, so once again, so which means, let us just write down the definition once again. Z of t, by definition, but please know that this is not a proper Fourier transform, because for it to be a proper Fourier transform, the integral has to go from minus infinity to infinity. It only covers one part of the spectrum, one half of the spectrum. So this has to be kept in mind. But one can nevertheless formally define a Fourier transform this way, such that the z of omega is basically x of omega, right? This is just to make this one consistent with the spectrum of the real random signal, right? So this is the Fourier representation of the complex analytic signal z of t. Of course, since z of t is analytic, all the rules of all the properties of the analytic functions follow. Okay, they will be single valued, differentiable, they're continuous, so on and so forth. So we can borrow all the tools and tricks from complex analysis to deal with analytic signals. Okay. Of course, here in this course, we won't be going into the finer mathematical aspects of these analytic functions. So we'll be using them operationally. Okay? We'll be using them as mathematical tools to do the calculations of relevance to optical coherence. Okay. Can I clean this part of the book? Yeah. Okay, so but x of t is real. X of t is a real random variable, a random function, or a random field, okay, which means, right? Of course, this is obvious, but why are we writing this down explicitly? Because we want to derive an important property of the analytic signals, okay, which means that's what it is. If x of t equals x conjugate, since it's real, then this follows from the definition of x of t in terms of its Fourier transform. Right? So which means this is it becomes plus I omega t d omega. Right? Now, here in the integral on the right hand side, let us just set omega equals minus omega prime. So what happens? So this becomes minus d omega prime. The limits flip the order, and if you get rid of, if you take into account this minus sign, it just becomes minus infinity to infinity. Right? This is what you get. So what does this tell us? What does this equation tell us? So the left hand side can be equal to the right hand side only if right. This is an important result, because what does it tell us physically? It tells us that the positive frequency part contains as much information as the negative frequency part, or the negative frequency part contains the same information about the system as the positive frequency part. So which means for the purpose of analysis, you don't have to consider both sides of the spectrum. Okay? You can just get all the information, all the relevant information about the system by just considering one part of the spectrum. So yeah, this is important. This that is true. That is true. That is true. So this is not confined only to optics or just in any real valued function. But in optics, we exploit this particular fact so that we just can study with just one part of the spectrum. And this is also carried through in quantum optics when we define this E minus E plus operators. So this naturally finds its way to quantum theory of optical coherence. So this is what it is. So of course, so just cleaning this part of the board. So now we will just write down a couple of formal mathematical results. This is just for the sake of completeness and to show that one can in fact use the tools from complex analysis, but we won't be going into the details. So x of t is just, right, if you want to express x in terms of z, it is just z plus z conjugate, which is just, right, or in other words, right. So formally speaking, you can also write down the imaginary part of z of t, and let us call that half y of t, some function, right. Now it can be shown that x of t and y of t, the real part and the imaginary part, form a Hilbert transform pair. Okay. There's something called Hilbert transform, and that is given by, we won't be using this particular idea in this course, okay, but we are just introducing this for the sake of completeness, and if you are interested, you can dig into the literature. You can go through the 3rd chapter of the book by Mandel and Wolf, Optical Coherence and Quantum Optics, chapter 3. Okay, this T stands for principal value. Now, Cauchy's have you seen this one in your undergraduate course on math methods or complex? Okay, so you do know that this P stands for the principal value, that notation, you're familiar with the notations. So this is how we calculate the principal value. Yeah. But so these two form a Hilbert transform pair, but we are just introducing them so that you know that they have a formal structure and a meaning. Okay. So, but the question is, okay, we have briefly introduced the concept of complex analytic signals. Why are they relevant to us? Which means, why do we use them in the study of optical coherence? Why do we use them in optics? So we use them in optics to calculate the correlation functions. So can I clean the board? Yeah, those online, can I clean the board, the whole board?
Yes.
Yeah, both sides?
Yeah.
Okay. Okay, so again, let's consider a source. it has a bunch of emitters. Okay. As usual, so let us say it just emits a field which is represented by this random function v. This superscript stands for real, because any optical field emitted by a source has to be real, a real quantity. Okay, and this r stands for the spatial coordinates, t is the time. Okay, so this r stands for the fact that it's a real quantity. Okay. So this v of rt is real classical optical field source of love. And this one is, of course, a random signal. Now, we can express this real signal in terms of a complex analytic signal. So how do we do that? Basically do the same thing that we did a few minutes back. So once again, we play the same game. So this one, V of RT, is the complex analytic signal corresponding to the real optical field V superscript R of RT. Okay. So henceforth, if there is no superscript, if we simply write something as V of RT, it means we are referring to the complex analytic signal. Okay. And if we have to describe a real optical field, a real physical quantity, we would explicitly put the superscript R. Okay. So which means, again, just we'll write down few standard expressions. This real field is basically given by V plus V conjugate, right? Okay, but how does this relate to some of the physical quantities of interest to us? So what useful quantities, physical quantities of interest can we define using these complex analytic signals? To begin with, the intensity of an optical field of a beam of light is related to these complex analytic signals. So the intensity is given by the expectation value of V conjugate V. Okay. Of course, this V without the average, if you just look at this one, this would give you the instantaneous intensity. So instantaneous intensity at RT, at the instant t with spatial coordinates, with the three-dimensional spatial coordinate r. Okay, but in lab we never measure instantaneous intensity. Okay, we always measure only the average intensity, because we measure the intensity over a duration of time, and that is given by the resolution time of detectors.
Capital T.
Some capital T r, you just let T run evolve over you just measure it over a finite duration of time.
The every detector will have some, some kind of time it will take for
True. Exactly. So which means you always measure only the average intensity. This quantity by itself is not the real physical intensity. So this can be related to the intensity. Okay.
It's proportional. Right?
It's proportional, right? And we'll see how it's related in a moment. And the reason now, this one should certainly, those of you who have studied quantum mechanics and seen some quantum optics books, this is very similar to E minus E plus, because the photon counting rate is given by E minus E plus. So this E minus in some sense corresponds to this V conjugate, and this E plus, the positive frequency. So this is the positive frequency part, and this is a negative frequency part. This is how we define the detection operators. Okay. So this one, the idea of complex magnetic signal can be translated to the realm of quantum optics in a very straightforward manner. Now, the other quantity of interest is cross correlation. This is an extremely important quantity that we will be using again and again in this course. Okay. So this is denoted by the letter gamma. It's called cross correlation because you measure how the field is correlated at two different space-time points. How the field at R1 T1 is correlated to the field at R2 T2. That's why it's called cross correlation. Okay. Now, this quantity quantifies the visibility of interference fringes. Produced by the superposition of the fields at R1 T1 and R2 T2. So this quantity will be extremely relevant when we study temporal coherence, when we study the double slit experiment. Of course, one can formally define higher order correlation functions too, but But throughout this course, we will only confine ourselves to 2-point correlations. But if you want, one can, of course, formally define but we won't be, so this is a 4-point correlation function, but we won't be using this quantity in classical coherence theory. But we will be using something similar when we study quantum optics, because over there, when we study coincidence detection, it will be a 4th-order correlation function, except that we won't have 4 different spatial coordinates. We'll just have 2 spatial coordinates and 2 time coordinates, but it will be a 4th-order correlation function. It will be E minus R1 T1, E minus R2 T2, E plus R1 T1, E plus R2 T2. Okay. But that's only when we do quantum optics, not right now. Okay, so I'll just clean this part of the board, and we'll see how the intensity of a real optical field is related to the intensity calculated using analytic signals.
Okay. In the experiment, how do they figure it out?
Oh, so
yeah, just
so the way they do is in the experiment. So all these things can be related to the spectrum, like, as you know, using the Wiener-Khinchin theorem. The spectrum is something that you measure physically through the spectrum analyzer. So from the spectrum analyzer, you can calculate the correlation function. So from that, of course, we can calculate everything, the intensity, depending on, we just need to set the delay to be 0 to calculate the intensity. Of course, then once you extract that value, there is this conversion factor that comes depending on in what system of units you want to express the result.
Also, it may happen that if you take the gap between T1 and T2 to be quite large,
yes,
then these, the correlation may not be reflected there, right?
That is very true, because the wider the delay is, the weaker the correlations become. So of course, for any meaningful measurement of correlation, the delay certainly has to be within the coherence time. So of course, that is something, of course, the experimentalists know that, because they know the source, the nature of the source.
Otherwise, it will not be reflected.
That is true. That is true. Yes. So can I clean the board, because I want to use the full board for the next stage? Is that fine? So again, the ones online?
Yes.
Yeah. So once again, we just write this one. We'll have this as a reference. Now, in coherence theory, I of r is proportional to So formally speaking, this is basically the time average. However, whenever we write down all these averages, statistical quantities, they are ensemble averages. Okay? So which means it's not always the case that the time average will be equal to the ensemble average. Though these two averages will be equal, provided the system, the process is ergodic. Okay? Of course, we will discuss ergodicity a little later, today or maybe on Friday, but all the optical systems that we will study are ergodic. We assume that they are ergodic. Okay, but however, I should like to mention that mathematically establishing ergodicity is not a trivial problem. It's quite involved. Okay, so we won't be going into the subtle mathematical aspects, but we do assume that the optical the random processes describing the optical fields are ergodic. So one naive hand-waving argument one could give is that the wave equation is symmetric in both space and time. Okay, so as a result, you can intuitively expect the dynamics, the evolution, the statistical properties to be symmetric in both time and space. So which means you could expect that the averages calculated over ensembles should be equal to the time average. But this is a very naive hand-waving argument. The formal mathematical analysis is quite involved. But it turns out that most of the processes that we are interested in within the realm of optics are ergodic.
Basically, if your optical field, it is more or less spread over the entire region.
True.
I mean, of this. So then, it will be kind of ergodic.
That is true.
It passes through all the region.
That is true.
Space and time.
Yeah, we assume that it's homogeneous in space and time. So that is true. That is true. So this is how this is the intensity defined from the coherence theory. And in terms of so this is not the real optical field. This is the complex analytic signal of the field corresponding to the real optical field. Okay. Now we know that from electromagnetic theory, this is the real intensity. Averaged over time. Basically, the square of the electric field. Now, let us show that so this is how the real optical field is related to the complex analytic signal corresponding to the field. We see this factor of 2 here. Okay. And you of course, you can sort of see why this factor of 2 comes, because whenever you write down the complex analytic signal, you only consider 1/2 of the spectrum. Okay, so that's why when you relate the intensity calculated through the complex analytic signal to the real intensity, the physical, the intensity, the physical intensity, this factor of 2 shows up. Okay, and of course, you can further show this IR is basically 2 times. You just ignore this. We can ignore these constants for the time, for the moment, but basically this the intensity from the classical electromagnetic theory is twice the intensity calculated through the analytic signal from the coherence theory. Okay, this. So how do we do this? This is a straightforward calculation, but it just involves multiple integrals. So now we are going to write V of R, V superscript R of RT in terms of complex analytic signals. So which means it is just of course, so we know what to do. We are just going to integrate out over T. That will introduce a delta function.
Excuse me.
Yeah. Yes, please.
Can you just write a little bit bigger? It's not having so much clarity while we are seeing here.
Oh, okay. You mean this equation, right?
Font. Yeah, that is fine, but from now on.
Okay, sure.
Thank you.
Yeah, sure. Is it okay now?
Yes.
It's clear?
Yeah, infinity it's a bit small, but the dW is fine.
I hope the integrands, everything is now visible to you, right?
And now it is visible. Thank you.
Okay. So this gives us a delta function. So we just enforce the delta function here. So that gives us V of R omega that's what we have, right? Now, please note, recall that we conjugate, because it's what we saw. X conjugate of minus omega is same as x of omega, because the positive frequency part contains as much information as the negative frequency part, right? So we are just going to enforce that one here. So this means this one, V of R minus omega is same as V conjugate of R omega, right? Yeah, just follows from this property. Just conjugate this once again and you get that one. Okay, so what does it give us? I'll just clean this part of the board. This is what we get.
Shouldn't there be a total negative sign?
Where is the negative sign?
Omega prime equal to minus omega.
This one?
No, in the
Here?
the minus 2 pi into
No, why is there minus 2 pi?
the omega is minus omega. The omega prime is minus omega.
No, I mean, no, I'm not making a change of variable in the integral. So here it is just delta of omega plus omega prime. But here we are just exploiting the property.
No, this part I understood. But in the integral, like
Why do you think?
you use the delta function to get to this.
So this delta function, when you enforce it, you just get rid of one of the integrals, correct? And
omega prime is equal to minus omega.
Yeah, omega prime equals minus omega.
Yes,
But then it's integrated over omega. It's d omega. So we're not making any change of variable. So we are not substituting omega minus omega prime for omega, nothing of that kind. Okay. And here you're simply exploiting the property, the fact that the negative frequency part contains as much information as the positive frequency part. And you're just enforcing that one here. So that's how we show that this, the first thing that we wanted to show, this is related to the square of the real optical field is related to the mod squared of the spectrum of the complex analytic signal. Okay. Now the next goal is to show that this one is basically twice integral 0 to infinity of the spectrum. So how do we do this one? So now so can I clean the board on the right side? So what about?
Yes, you can, please.
Yeah. So now the equations symbols are legible, right? They are big enough for you?
Now it is clear.
Okay, thank you.
Thank you.
Okay. Once again, what you're going to do is we'll split this integral into two parts, the negative frequency part and the positive frequency part. Now, let us consider this integral, the one involving the negative frequencies. Okay. That omega equals minus omega prime, which means, right? So here you have a minus d omega prime. The order of the limits will get flipped. So here you will get if you get rid of this minus sign. If you want to get rid of this minus sign, we are going to just flip the limits. So this one is basically V of R omega, and this one is basically V star of R omega. Once again, we are making use of the same property, that the negative frequency part is the same as the positive frequency part, correct? So what does this become? So when we add, it just becomes so these are standard relations involving complex analytic signals and their Fourier transform. So we will be using some of these relations over and over again as the course progresses. Okay, so now we have shown this one. So any question? So any question online?
Excuse me?
Yes, please.
In the final expression, it should be 4 pi, or where that pi?
Oh, you mean, one second, hold on. Yeah, so basically it's 2 times 2 pi. Yeah, thank you. Yeah, so just wanted to show that this integral from minus infinity to infinity is twice the integral from 0 to infinity. So you're right, 2 times 2 pi. That pi still remains there. The 2 pi remains there. Yeah. I'm sorry. Thanks for pointing this out. Yeah. So any question? Okay. So can I clean the right side of the board?
Yes.
Yes.
So we have shown all these things. So 1/2 of the task is accomplished. The next thing to calculate is this one. Because this is related to the intensity. Of course, eventually there will be an average, but this is related to the intensity of the optical field calculated in terms of the analytic signal from the theory of coherence. So now recall that oh, by the way, those attending online, if you feel that my handwriting is getting smaller, please bring it to my attention.
Good.
So we are simply going to substitute for V and V conjugate in terms of their Fourier transforms into That's what we're going to do. Okay. So I'll just wait for a minute and do the calculation on the right side of the board, because I don't want to erase the one on the left side. So whenever you're ready, I will erase the right side of the board. Can I just erase this portion alone?
Yes.
Yeah.
Yeah.
Oh. So now, so we'll have right. So once again, in the integral involving the negative frequency spectrum, we're just going to play the same game. Set omega equals minus omega double prime. Okay. And when you do this one, you will get one second, grab omega. Should one second. It should be, it's omega equals minus omega prime, so it should be minus omega. Omega prime.
Won't be a
Oh, yeah, I'm sorry. No conjugate. I'm sorry. No conjugate, my bad. D omega prime. Oh, okay, that's much, yeah. It's dt here. Minus omega prime. Yes. So that's what it gives us. So we enforce the delta function. We get a factor of 2 pi. So once again, this one. V tilde of r minus omega is same as V conjugate of r omega. Okay, so that's what it is. Now, if you multiply this one by 2, then so multiply by 2, you get this one. Okay, so you see that, of course, once this is done, all we have to do is to calculate the average. Okay, and once you take the average, that gives you the intensity. That will relate the intensity calculated, the intensity of the real optical field calculated from classical electromagnetic theory to the intensity calculated through complex analytic signals from the coherence theory. Okay, and that will tell you that the real intensity is proportional to so, right? Any question? So, is this clear? So those online, any question, comments? So is the algebra clear? So we'll stop here.